Alright, hello everybody, and welcome back. So today we're going to be basically doing a review and conclusion of our first project, right? So what we worked on before was we introduced our project, and I told you guys, alright, go work on it, right? I don't want to see your face, just go work on it, right? Yeah, so that's effectively what happened. And now what we're going to be doing is I'm going to be showing you what I made, right? I did the project along with you guys. And so, yeah, I'm going to be showing you guys what I made. And I'll go through basically two different sections of this video. First off, I'll start by introducing you to the design and walking you through each component and why each component exists, how it does. And then, I'll go through how I went through the process. And then secondly, I'll go through a design review. So I'll go and talk about, from a neutral perspective, what could be improved, right? What can be improved and what can be changed, right? What can be made better. Because there is always something that can be made better, even if you don't see it. But looking at something from a neutral perspective is a really, good way to see something that can be improved and to move forward from there to improve it. Now I only spent like 3 to 4 hours doing this, right? If I wanted it to be perfect, I would have spent like 6 to 7. Good CAD takes time. It really does. And that's inherent in the fact that you don't really notice everything instantly, right? The more time you spend doing something, the more you're going to notice and the more you're going to learn. But yeah, so right, I spent like 3 to 4 hours. Honestly, that's not that much time to do a whole design from start to finish. Most of that time, like probably 3 of those hours were in CAD, and then the first hour was just thinking and concepting, right? Actually, that was probably only the first 30 minutes to 20 minutes, right? Like I was doing sketches, figuring out, okay, where's everything going to go? Where's everything going to mount? Feasibly, like, what's the layout going to look like? That's the general concept. And then, like, will this thing actually work? Because sometimes you don't know until you draw it out if it will. And then you get more detail as you move into CAD, but drawing it out is a good first step. So we'll go here to our team, right? And I'll go to off-season 2020, and I'll go to my folder, and we'll go here, right? We'll go to our projects folder. Now I got the activities folders. That's going to be full of all the activities I've been doing, because I have been doing like multiple of each one, both practicing, developing them, and also filming these videos. But yeah, we'll go to our projects folder, and I'm going to go to Project 1, 2017 ball intake, right? 2017 ball intake, and that was the task, right? Reviewing the task, actually, let's do that real quick. Right, what was our task? And I'm doing this because keeping the task in mind is super important, right? Like, what is your task? How do what does it mean, right? And how can you fulfill that task? That's what you figure out when you're designing. But right, identifying your task is super important. So the task this time was to intake balls, right? Get them from the ground onto the robot, and then these little yellow wiffle balls from 2017. And I'll link the game reveal video from 2017 in the description so that you guys can watch that. So we looked at some existing working solutions. I took pretty heavy inspiration from the Robonauts design, although I'd used some different geometries, some different configurations. Tried to make it a little bit simpler. I'll also link this playlist of robot reveals, that way you guys can do your own research when you're viewing this, because doing research is an important part of design as well. It's one of the most important parts, because identifying the task and then identifying how other people have done the task is that's the way it goes. Yeah. But yeah, so basically the task was to intake the little yellow wiffle balls from 2017. That's the gist of it, from the ground onto your robot. So here we have our intake, right? Here we have our intake, and we can see that we have, starting off, it's a very basic design, right? You've got this shaft, which is spun by this motor, right, by a chain. They're connected by a chain. And when you spin this motor, the shaft rotates. And this shaft is going to have wheels on it. And these wheels rotating will, if we go ahead and select like this face here or something, we can rotate this around, and we can see, right, like this shaft can rotate around, and it would actually be going the other way. The shaft rotates around, and you've got wheels, you've got a ball that gets sucked up in there, right? So if we go to our demo configuration here, we can see that we've got a ball that's attached right in here, right, and it's just sliding along this ramp, moving upwards. If we go to the right here, we can see. Here, I'll do a section view so we can see it a little bit better. Move this down a little bit. Yeah, just like that. All right. Right, so we can see that if we go here, this ball can move up and down along this ramp, like up into the robot. That's the gist of it, right? Starts on the ground, your robot rolls up to it, and pulls it up this ramp right into the robot. Right, so I'll turn off the section view there. It's kind of killing my computer, but yeah. And we'll go to our ramp config, and we'll go from there, and we can start to analyze this. So when I did my workflow, I'll go through my workflow first, right? The first thing I did, right, was I made a sketch, and I sketched out everything that I was going to want to do, and I worked through that, right, until I had sort of a layout that mattered, that I liked. So I did pretty much like a top-down sketch from here. I was like, okay, so I want, this frame cut out here, right? You have to have this much space for bumpers in the regulations, but I put this frame cut out here, and then I had a shaft mounted here with rollers on it, and then a motor. Oh my God, what did I do? Oh, I made a new tab by accident. Yeah. Okay, so I had a shaft right here with rollers, right? And then that connected to a chain, and then that connected to the sprocket, which drove this roller shaft, right? And then you got some sort of backplate with some sort of adhesive or like sticky compressible material. In this case, it would be like a yoga mat or something, like a cut-up piece of yoga mat would work very well for this application, because these wheels are also compressible and a little bit sticky, right? They're squishy. These are Andymark green compliant wheels, and the green ones are the squishiest. That's a common fact. But yeah, so that's the gist of it, right? And I did that in a sketch, right? Because working through, especially with common off-the-shelf components, like where you have a set, this is only at a set height. Right? This component here is at a set height, like you can't change that. And this height matters, right? Because that's the height that you come onto the ball at. So figuring out that spacing before you're constrained and tied down by common off-the-shelf components is super important. So the first thing I did was I went ahead and I made a custom component. I made a custom side plate that housed all of the geometry I wanted. And we'll go here and I'll show you guys that. So it's going to be here in intake, and it's going to be in intake side plate. Right, this is the side plate here. If we switch our configuration to our right side here, we can see that there's a hole here for a bearing, and there's a hole here for another bearing with motor mounting holes around here, right? That would be mounting for a versaplanetary with some sort of motor on it, and there would be a chain running between these two. That's the basic gist of it, right? And then this spacing from here to here is determined by, it's driven by where you want your rollers to be in proportion to the ground, which is also in proportion to where the ball is. But yeah, so I'll go and I'll look ahead and I'll go to this context. Now this is going to be an older context, so this assembly is not going to be updated, right? This is an older version of the assembly. This bar is closer, and this thing here, you can see how it's mounted, right? You have a flange coming out for the mounting here, and a flange coming out for the mounting here. That's the main gist of it. If we go to our left side configuration, actually no, our left side configuration wasn't on there, right? Our right side configuration, just like that. And then you would have a roller, right, coming out of here, and then your motor would either be coming out this way, if it can fit, within this space here, or this way. And the problem with it coming out this way, actually, is that it wouldn't be able to, you'd have to extend this frame, because if you wanted to intake balls there, they would come up and they would hit the motor as it came out, right? If you've got some sort of, if we go into drive and ball pathing, right? If you've got some sort of versaplanetary like this, and it's mounted on the, if it's mounted on the, on this bracket here, that would be sticking out this way, you're going to block your ball's path. And I'll show you, let's see, we also have, yeah, so here's our ultraplanetary as well, and you can see that's sort of the same format, right? Short little gearbox and a motor on the end. That's the thing. So if we go to our assembly here, go back to our assembly, this is actually in the drive-based context, but we'll go here to our full assembly, and I'll overview a few more things about this design, right? So, all right, we've got our Snowblower motor here, which drives the sprocket, which drives this roller here, and then we've got we've got these common off-the-shelf brackets here. These are from Andymark, common off-the-shelf brackets that hold this this roller shaft on. And right, so the first thing I did when I figured out the geometry, the next thing I did after that was I went ahead and looked. I was like, okay, so how can I get this geometry into a thing that's actually practical? Of course, you could make the intake side plate, go ahead and insert this in as a reference. You could make the intake side plate. It's not, impossible to do, right? This is just a sheet metal part. There's a flat part, and then you bend this flange out, and you drill a hole in it, and then you bend this flange out the other way, and you drill a hole in it. They're 90-degree bends in 1/8" sheet metal. It's not impossible. It's actually pretty easy to do, and there are ways to represent it in CAD so that it has like a flat pattern, right? Like you'd have something sticking out flat, so you could, use that to cut it and then bend everything. There are ways to do that, but I didn't actually want to use something like this because you don't need it, right? Like you have something that you can buy, and that's much easier than just making this. You can make it, but you don't have to. And so, you want to give mechanical team the easiest job that they can have. Of course, that shouldn't be at the expense of your design working. I do have a custom sheet metal part here, and that's to mount the motor here. And there's a very good reason for that. The reason being, there is a custom part to mount that motor. I'll go ahead and delete that. There is a custom part to mount this type of motor, which is a snowblower motor. You can see it's got a little motor shaft down here, little motor can. Then you've got this thing coming up in here, and you can see the geometry. It's a, you've got your lead screw, right? You've got a worm drive, which is just like a screw, basically. And then you've got a gear in here, and that screw spins this gear, and it gives you an output of about 100 RPMs. So it's 100 revolutions per minute. That's a really good speed for an intake like this, and it gives you some good strength on that snowblower motor. So that's a cheap alternative, and I also chose it because, because it fits within this frame constraint, like what I was talking about before. Otherwise, you'd have it sticking way out, right? It fits within this frame constraint, and that's very important. It's also not too large. Like, the size is up and down, and that's much better than it being side to side. But yeah, so the reason I made this sheet metal part here, right, and this is mounted with standoffs, right, because it has to be a little bit away because this motor comes out farther than the mounting holes, which seems like a silly design choice, but that's how it is. But yeah, so you've got this, right, this is a very simple thing. You've just got holes here to mount to the chassis, and then you've got holes to mount to the motor. It's a very simple part. If we go and we go to our components, right, and we go to find our snowblower motor mount, which there's the motor itself, right? Here's the mount. You can see that this mount is actually, right, it's up and down. The triangle is up and down. And if you look at our snowblower motor, right, that would stick out sideways. And we don't want it sticking out sideways, we want it sticking down. Because that's much easier to manage space-wise, and I don't want to give all the other designers a hard job because I decided to take up too much room with my design. Like, that's kind of a dick move, right? You don't want to do that. So you want to, use as little space as possible, especially on a robot like a 2017 robot where, like, most of the space inside of the robot, inside of the frame, is dedicated to storing balls, right? You want to be able to do that as effectively as possible, so something that's sticking way up isn't going to be ideal, right? So that's why I didn't use a COTS component there, instead using this. And it's also fun to give mechanical team, a few headaches and nightmares, but also, learning experiences and jobs, right? Them having jobs to teach new mechanical members is pretty important. So yeah, but also, they should have something to do. That's at least the mentality there, right? And then I've got this, this back plate here, which is just designed out of polycarbonate, and it mounts off of this central support. And this central support actually has a few functions. First, it serves to mount this back plate off of, right? As I showed before, right, the ball kind of rides up that as it goes into the robot, and these sort of it acts sort of like a revolving door, like it spins this, these spin, and then they make the ball roll up this ramp. But then you've also got this cross member here, right, which acts. It also has a few functions. The first function being to mount this back plate, right? You've got a bunch of rivets mounting that. And then the second function being to strengthen your drive base. That is really important, having a strong drive base, because this drive base, without this, if we go ahead and hide this, I'll show you, right? Without this, the drive base, if you if you went on top of it like this and you squeezed it this way, that would be bad because, it would kind of become a triangle, and you don't want a triangle drive base, right? You don't. Right, you want a drive base that works, and the wheels shouldn't be pointing inwards. So you want some sort of structural frame member there, right? And if you have a cutout in the front, you usually need that behind the cutout. That's the idea, at least. And then it also acts, like I said before, to mount this backplate here. Okay, so that's basically the overview of the design, right? Like, I didn't want to, make it too complicated of a design. It's quite simple, actually, right? Just got shaft mounted by bearings. You need bearings for rotation, usually. To these, common off-the-shelf brackets, and these common off-the-shelf brackets, I decided to use them because they sort of gave me the geometry I wanted. That's what you're looking for. Finding common off-the-shelf parts that fit the geometry you want is pretty important, and it's one of the longest processes because you have to sort of look on different websites, try different files out, and just see what's what. That's why making custom components like this is sometimes the way to go. And if you can't find something that will do what you want, sometimes you have to make a custom thing. That's just the reality of it. But yeah, so right, I've got a COTS component here, shaft here, and then these anti-mark compliant wheels are COTS, and then these things in between them. This is actually duct tape, just a CAD representation of duct tape. That's what we use in our design, and it actually works really well, right? It serves to keep these from moving axially with the shaft, right? It serves to keep them from moving this way, right? Just sticks onto the shaft, and then we wrap it around till it's tall enough to keep the compliant wheels from moving. Saves us a lot of money on shaft collars in between all of these, and the spacing doesn't need to be precise, so we just cut like roughly an inch, right, and mount them between each other, just like that. Now, I didn't spend too much time editing the drive base for this, because if I wanted to design a good drive base for this game, I would have. This is not really an ideal drive base for 2017. You'd want smaller wheels, gearboxes farther back or lower down, basically just give you as much space inside of the drive base as possible. But that wasn't the task. The task was just to, make this mechanism and design it, in a drive base context, but without doing much to the drive base. Just make this mechanism feasible, right? Make it so that it can work. Make a mechanism that does this task. Right, so you've got this, and that's basically how it went. So now I'll get into the second portion of the video, which is just a design review. Right, it's just a design review of the concept that we had. So I'll be looking at this from a neutral perspective, and I'll say, some pros of it, some cons of it. Right, what could be better? What could be worse? What's bad? What's good? And what could be improved, right? Good, bad, and the ugly. Although I don't think it's too ugly. I like the little green accents here. Yeah, but so starting off, right, from a neutral perspective, and this is the role-playing portion of the video, right? I'm stepping into somebody else's shoes, although it is role-playing in that, I'm being somebody else, but I am, alone in my bedroom filming this, so it may have other connotations. I'm just going to use the word, design review for now. But yeah, basically, right, I'm just going to come at this from a neutral perspective. So, starting off, what are some things I see? All right, does it fulfill the task is my first question, and I think it would. I think it would, because you have, this geometry looks pretty tried and tested. You would have to test this in prototyping, and this mechanism you would want to prototype this mechanically pretty heavily, because there's many things that you need to test mechanically, like how squishy are the balls, how compressible are the balls, how compressible are the balls, how much squish do you need on the balls, right? What material should you use for the compliant wheels? Like, there's different colors of compliant wheels with different hardness ratings, and this, like, the green ones are the squishiest. That's common knowledge, but the green ones are the squishiest. But you could test, should we use harder ones? And then should we use, maybe smaller compliant wheels, or move this up? I would say it might be good, because this ball is almost touching this shaft here. You'd probably want to move this up about an inch just to offset it so that this spacing worked a little bit better. You'd also want to test if a yoga mat backplate here really works to draw the balls in. I don't really see a reason why it wouldn't work, as long as it's sticky enough to sort of grab onto the balls. But maybe stuff slips out, or maybe stuff jams. That's possible, right? That's totally possible. So it's worth looking at, does this actually work, right? And that's something you want to test in prototyping. First, you test feasibility, like, does this work? And then second, you test, specific things like spacing and material choices. All right, next thing I noticed about the design, I like the use of the Snowblower motor. I think it fits pretty well with the design. One thing I would say though is that it could be moved over to the other side, right? This snowblower motor, if you flipped it around, and I'll go ahead and do that real quick, right? Paste that in. If you flipped it around, we'll rotate it 90 degrees, 180 actually. If you flipped it around, it would look like this, right? The little shaft end, the little motor end, would be sticking out the bottom. And so if we move it to this side of the dry base, right, we could tuck it in there all nice like. And I think that might be a better use of the space than having it sort of, come out behind this crossbar here. You can move the crossbar back like a half an inch, and then put this snowblower motor down in there, and that would save you a little bit of space horizontally. And I think that could be a better use there. So that's one thing I would critique, a little bit of space wasting there, although it's really not a huge issue, right? You save like 2 inches from doing that. But if that, is a 2 inches that can be used somewhere else on the robot or with some other mechanism, then it's worth doing, right? Yeah. But yeah, another thing, like I said before, actually, so that wouldn't be one more thing, but you would want to offset this upwards. This is too much compression. Even with prototyping, like this isn't even worth giving to prototyping because you'd just be breaking something. You'd be bending this shaft or breaking these rollers, or like the squish is good. You want like an inch to a half inch of squish, but having squish to the point where the ball touches the shaft, that's not the best. So this is again more of a nitpicky critique. The whole thing as a concept works well. But yeah, I would include some sort of spacer here, either moving this a half inch up or an inch up. And that would be pretty easy to do. Honestly, it would not be that hard to do. So it's worth doing. But yeah, so including some sort of spacing there so that it fits a little bit better. And then you can work to use that spacing. You can work to use that spacing to yeah, so it wouldn't be that hard to do. Just to add some spacing in there to give this a bit of an offset. And then you could also move this pipe back here, right? If we go ahead and edit this in context here, we can see how this backplate was made. And that's basically just using the geometry from the part, right? If we go to our second sketch here, we can see that we've got the radius that we want to sort of follow, right? So 6 inches, or the radius here is 12, right? The ball is 5 inches, and then this is a 1.5 inch wheel in radius. It's a 3 inch wheel in diameter. So 1.5, you want like a half inch of compression or squish. Maybe 1 inch would do actually, because these are pretty squishy. So 6 inches is a safe radius to go by. You can see that you would probably want to, because this is going to be below, like you want to move this up like a half inch, just so that the this ball will fit with this. And then you can see that this was modeled to be to have the same center and to also fit there. And you would want to also move this back and have some sort of bigger radius between there. If we look at a dimension here, between here and here, that's too small, right? 3 inches, that's not enough for a ball. That's 5 inches in diameter. Even if you have a half inch of squish, that's still giving you only like 4.5 inches. That was like roughly 4 inches that we saw just there. So that's not going to be enough. If we check that and we go back to our assembly here, right, we can sort of conclude. So 2 main things, right? Figuring out spacing for the motor a little bit better. It's not a huge nitpick, but it's a little bit of a thing. Figuring out some sort of spacing for the motor, some sort of spacing alternative, and then also figuring out some sort of better spacing for this here and here, right? This ramp here and here. Another thing I might say is that these would be a little bit weak by not having a T-gusset on top. And I get why that's done, because this has to come over and mount to this, and the T-gusset's not long enough, right? It's not the same length. So there would be like an overhang, and you don't want that. You could fill it with spacers, but you don't need to. And this front plate here it's really only to hold a bumper. It's not to do anything super structural, so you don't really need to worry about that. And then I think the last thing is maybe I would worry about this catching on the ground if it's just polycarbonate, and I'm assuming it would be deformed, like bent somehow with heating. like you know put a heat gun all over it and then bend it into the shape you want. I would figure out maybe some way to support it off of this frame on the front there, or maybe just make sure it doesn't, you know, scrape along the ground so that like when you're driving along this way, it doesn't fold over backwards and your whole robot does like a wheelie over it. You know, that would be bad. That would be bad juju. That would be no good. But yeah, so figuring out some way to maybe support that could be important. Again, that's something that would be tested with driving practice and prototyping. But yeah, overall, you know, this is just a sort of a design review of this mechanism, right? Like what it was sort of designed to do, right? We started with the task, then moved through some of the workflow that we did, or that I did, and then I, you know, went through the final product that I came up with, and then we did a design review. That's going to be basic standard procedure for designs, and it winds up resulting in a design that's, you know, a little bit more polished and a little bit more effective. But yeah, so again, if you guys have any questions, thank you, you know, and please ask them. I don't know why I thank you guys, but if you have any questions, thank you for having them, because that was nice of you. But yeah, if you have questions, please ask them. Don't hesitate to ask. I will do my best to answer. And this project, you know, sort of a first project. It's okay if you guys, you know, were a little bit off the mark with this. Right? There's no right answer, but there are wrong answers. I'm not gonna lie. So if a few hints, for if your design is not really doable. First of all, like if you can't make it, right? If you can't make it in real life, it's not gonna really work out. And second of all, if it's, you know, if you can't use it, if it's not usable, if it doesn't satisfy the task. So usually the major pitfall is that it satisfies the task, but you can't make it. Like, you know, you'll see people make like, you know, some sort of big, huge, complex part that, you know, they didn't really think about how that would actually be made mechanically. And that's okay, that's normal. That's what I did. Like my first year, I was asked to design an intake, and I designed something that was completely abstract and didn't make any sense. It would have satisfied the task, but there were no common off-the-shelf parts on it, and it kind of didn't really, it wasn't doable. So yeah, that's totally fine. Figuring out ways to make it doable, that's most of the legwork with CAD. So yeah, we'll work on that a little bit more in the future as we get into some more projects and some more complex projects. But yeah, thank you all guys for watching. Again, if you have questions, please ask them. And I will see you all next time. Bye.